Thank you for noticing this. I almost forgot. Well, I did forget, but gladly you mentioned this. All right, so you now see, here we are, this is the situation, and the cost is that, and let's assume that xn is 0. So we are in a feasible, basic feasible solution point where xn is 0. The cost is something, let's call that cost is, let's call that z for argument's sake. And now let's suppose that this is a point we have found, and we want to find out whether this is an optimum point. And I'm not going to try and prove the theorem per se. I'm going to just give you the intuition about why it's why this condition, where does that come from, that c hat n, and why does it have to be positive? So let's say that we move from this point to another point. So we assume that we have so we have another feasible point in which we are moving from x to delta x. So delta x is a small change. We are moving a little bit in some direction, right? And it's a feasible point. So we are moving in that direction, just a little bit. Now, if we look at what happens here, so I'm going to write it like this. So we have here we have the delta xb, and then we have takes a little while for it to update. I'm wondering why it's not updating it yet. So the idea is that the delta x is here. Why is it not updating? It should update. Let me try it again. Damn. I was using this. No, okay, now it's better. So we have this situation where we are moving from x to delta x. So of course, obviously the delta x is delta x, but then also we must have this must be feasible. I mean, obviously, when we are, sorry, it should be capital delta. So obviously, when we are in this x plus delta x, that must be equal to b. So that because if we rewrite this, I'm writing that. So this is if and only if right? Because this is linear, so we can write this. So this is feasible if we are doing this. So that So the thing is, we want to look at what happens in this new point where we are looking at. So let's look at this. Let's look at the cost function in this point, at this point. So z at this new point, and let's call this y equal that. So I'm using the same part here. So this is y is that. So z y, that cost is zx, right? No, sorry. All right. Now it's again, it's the C transpose, sorry, y, which now can be thought of as, I'm going to write this once more so that, write one more thing here. So because this is so, then we can write also that a y is b, right? Right. Okay. Now, if we look at this, and that is also oh, sorry. Also, we have that we can now skip this, split this y, which is the x plus delta x. We can split it into two. We can write that as C transpose, and then we can write this as y b. Sorry. Y n, keeping in mind that that's right. So we're multiplying these, and we can write this as and we can split this C also into this B part and then this N part. So this becomes C, sorry, C B transpose Y B plus C N transpose Y N. Okay, so there is the part in Y which comes from the cost that is in the basic solution, and then the cost that is in the null solution. And now remember, this null part, this yn part, is not necessarily zero. So it could be zero, obviously, but maybe it's not. I mean, we don't know. And what happens here is that we want to look at the net effect on this cost function when we are moving towards this point delta x. And what we want is, we want to make sure that this cost function now, when we move a little bit, right? This delta x is a little bit. And when we move into this other point, we want to make sure that the cost doesn't become smaller, right? We want to make sure that that doesn't happen. So what happens when we move by this delta x, and it's written here in this part that ax plus a times delta x equals b. I'm not going to go there. I'm going to just look at this net effect, because when we change this x a little bit, both the null part and the b part may change, right? And if we are changing this null part a little bit, then also the b part must change, so that the net effect on this ax equal b, this a delta x must be equal to 0, right? Because this a times delta x must be equal to 0. So I'm going to rewrite this part. I wrote ay equal b, but I'm going to write it like this. So I'm going to write this as b times delta x b plus n times delta x n is 0. It hasn't updated it yet. So you see here, this is what needs to happen for us to maintain a feasibility. So the B part, the basic part, and the null part must offset each other in here. So, so when we move in this way, so we're moving from x to y, then the change must be, a proportionate change in the null part. There's the basic solution and the null part. And when we change these ones that were 0, we change them to non-zero, then also these need to change to offset so that the ax or ay is still equal to b. And this then, on the other hand, causes a change in the cost function. So if we look at the change in the cost function, then we can look at the x minus y, right? Sorry, zy minus zx, right? This is the change. How does the cost change, right? So that would be CB transpose. And now I'm going to write here XB plus delta XB minus, and I'm rearranging this CB transpose XB. I hope you're going to see where I'm getting at, plus CNT times XN plus delta XN minus CN transpose X n. So that's how the cost function changes when we move from x to y. So the new cost is zy, the old cost is zx, and then I've just rewritten this and we changed this a little bit so that it changes into that. Now this is all linear, so really the change is C transpose, CB transpose delta XB plus CN transpose delta XN. Right? So this is the change in the cost function. But remember now, we also must have that B times delta XB plus N times delta XN must be equal to 0. So let's just all express this in terms of this, this change, this delta XN part, right? This delta XN. Let's just figure out how that is. Because if this is true, B times delta XB plus N times delta XN is 0, then we can write this in such a way that I'm changing this in the middle here. I can write this that B times, sorry, I can write that delta XB is equal to B inverse times, sorry, it's the negative of B inverse n delta xn. Where is that? It says invalid equation. Oh, there's a typo. Okay, that should be fine. All right. So we're seeing here that this delta xn can be replaced by that. And now I'm going to just punch it into this latter part. So I get that, I make 2 here. So all this points to that C B transpose and I'm going to write here minus CB transpose B inverse n delta x n plus C n transpose delta x n. So this zy minus zx is equal to this. So this change, this is the net change in my whole cost function. It's minus CB transpose B inverse n delta xn plus Cn transpose delta xn. And what does it say? It says that when we move in this null part just a little bit, this delta xn is now the little change in those that were now 0, right? Delta xn means that there's the basic solution and all these other components were 0. And this delta xn means that if we move one of these a little bit, then what happens to the cost function is this coefficient here. And if you look at it really carefully, let's just rearrange this a little bit. So I rearrange this just a little bit and I take the xn on the right and I write it like this. Oh, that's not capital C, it should be small. All right, so we have here C, I rewrite it just in transpose minus B CB transpose B inverse n delta x, right? So we see here that these are the Cn transpose minus CB transpose B inverse n are the coefficients for delta x, and these determine how the cost function moves when we take one of those components that is 0 and we try to change them. And now comes the feasibility part. Look, it's only feasible if all the components are positive, right? And if all the components, remember all the B components are positive. So they can come down or up, don't matter which way they go. There's always room to move a little bit of those. But the delta x, the xn part, they are all 0. They can only move in one direction. They can only become positive from 0. But if all these coefficient components here, this determined by the Cn transpose, Cb transpose B inverse n, if all those, that's a vector, and if all those components are positive, then the cost function can only increase if we change this delta x, if we change those null component, those 0 components. If we move any of them up, then what happens to the cost function? It increases. This means, look, we know that there's one thing you have to understand. We know that this problem is convex. And because it's convex, then if it has a local minimum, then that minimum is a global minimum. This is a local minimum now because trying to change this point, even just a little bit, if all these coefficients here that are determined are positive, then it means that even if we try to move into any feasible direction, the cost will increase or stay the same, but it doesn't matter, it's local minimum, meaning it's optimal. Yeah, that's the point here. That's the point we're trying to make. So we have some of the components are non-zero, some of them are zero, and any change in these components that are zero can only be positive. And this determines, oh, sorry, there's one delta x in, right? Yeah, so that's, it's really important to understand that we're dealing with the net change in those. We look at what happens if we try to increase one of those or some of those numbers in those components. If we try to increase them, then the cost will increase as well. So if this is so, then this must be the optimum. And that's the point of theorem 3.10. That's the key issue in 3.10. All right. That's what I wanted to say. I mean, last time I talked about this, I stuttered a little bit because I didn't have this. I couldn't write it like this. I'm sorry that there's so much. Maybe I put a little bit of room under here. So put a little bit of extra lines here. Yeah, I think that's a bit more readable. Let's probably make it a little bit more airy. Okay. So we looked at this change and we noticed that what happens when we try to move from this optimum point is this is the zy minus zx gives the change in the cost function. If this happens to be, if this change is positive, then we are in an optimum point. I think that's the fascinating part of this theory, really. I mean, if you figure out that this is the way it goes, you know, changing that, the matrix coefficients kind of work as an intermediate because ax must be equal to b. So change in here causes some changes in here, so that that balances it. And then using the cost vector to assess what happens to the cost function, if we notice that it will always become, it will always increase, then we found the optimum. Right. Okay. So I'm going to, sorry, I forgot to restart again. Sorry, I shouldn't take these breaks. So here's the algorithm. Let me just restart from this. So the algorithm is given as follows. We choose the feasible basis. We find the reduced cost. If the reduced cost is positive, then we stop, because we just proven that if the reduced costs are positive, we can stop and the basis is optimal. If not, then one of those reduced costs components is negative. It means that when we take that corresponding component from the null vector, the xn part, which is now 0, and we increase that, then these will move a little bit, somehow these basic parts, and then the cost will go down. Now the cost will go down when we increase that one null variable, and the cost, how much it goes down is proportionate to the corresponding component of the reduced costs. So let's call that AS. It's the S column. So it just means that, you know, it's this, the vector, the unit vector that corresponds to this component alone. These are my left hand. These are the basic vectors. They move when I move in some direction when I increase this. Here it's 0. Now, now we compute the net effect on these basic variables of increasing this one null variable. We know that when this increases, because the reduced cost is negative, we know that the cost will go down, and this B inverse A, this one, you know, it gives us the net change that has to happen here so that AX is equal to B when we move from here. If all these changes here are negative, then what it means is when we go here, this will increase, right? This will increase, all of these will increase, and it means that it's unbounded. We can go in that direction and every single thing will just decrease. I mean, the cost function will decrease, and these basic variables will increase, and there's no problem. None of them will hit 0, and we have what is called an unbounded problem. Otherwise, you know, from this net change, the net change that for increasing this, these have to change. This is the net AS star is the net change operation here. So if it's positive, it means that one of this will go to 0 at some point. And the 7 we compute, when does it hit 0? Which one hits 0 first? So if you look at this formula, it looks a bit hard. I'm not going to derive it here now, but the meaning of this is that this AS, sorry, this AS star J that is mentioned here, that is minimized, AS star J is the jth component of when I increase this, how much does this change? And this XBJ is really the current value of it. The current value is here, and by moving this by 1 unit up, this goes down by, let's say, this much. And we divide this XB with XJ. It means that how many units can this go up before this hits 0? And we find the one that where this proportion is the smallest. It means we find the component of the basic vectors that goes to 0 first when this increases. This is the R here. This is the R, XBR. It means that, let's say this is R, it means that once this increases, then this component will be 0 first. I mean, others may decrease as well, but this decreases proportionately fastest. So this is here, this is at 0. This means now that we change this particular null variable and this particular base variable, which switch their places and start again. We now have a new basis, one that produces a smaller cost. We go to step 2. Now, let's see what happens here. We've now taken one null variable and one basic variable and changed their places and gotten a cost that is strictly smaller. So we can keep doing this until one of two things happens. One, I find a point or a basis for which the reduced cost is positive. It means we cannot make it lower. Or two, we find out that there is a null component that we can increase while all the basic components increase as well, and the cost goes down. So we found an unbounded solution, or unbounded situation, so the problem has no solution. One of these things is going to happen. Why is one of these things going to happen? Is that at all times we have some set of basic variables, right? If we have some set of basic variables, then we have a particular cost. Whenever we come up with a new set of basic variables, so we don't settle here if this is not optimal, and if we don't figure out that, okay, here it's unbounded, we find a new set of variables, one that has strictly smaller cost. So the cost cannot go down because it's, you know, when we have a particular choice of these basic variables, then it has a particular cost. The cost is uniquely determined. So we only try a set of basic variables that has a strictly lower cost. There are only finitely many of those. So either at some point we've tried them all. So, you know, it's impossible for us to find a new one with a smaller cost because we tried them all. So that must be the minimum. Or we found a minimum before that because of the reduced cost. Or, well, we found an unbounded solution. Strictly speaking, there is one problem, one situation, and that is when the problem is degenerate. If the problem is degenerate, that this is not covered in this situation. So strictly speaking, the possibility that one of the basic variables turns out to be 0 exists. This possibility exists. And if this happens, then we are kind of screwed. This proof doesn't cover that situation. So let's assume that no degeneracy happens. There are ways of tackling degeneracy, but they're out of scope here, because I think the most important here is the line of thinking or the way of thinking about this algorithm. Okay, that's what I wanted to say about the simplex algorithm. And, you know, I think you can understand the simplex algorithm if you just try it by hand. There is an example, and I'm going to show it to you. Example 3.12. So there is the code in the Moodle. So I would suggest that you guys, I'm not sure, do you have, just as a very quick question, do you guys have access to MATLAB, you know, just now? I'm going to pause this.
Yes.